So we're going to start talking about stoichiometry today. And stoichiometry is really just a big long word that means chemical arithmetic. So what we're going to be doing is using balanced chemical equations, and then given information about a reactant or product, we can determine information about another reactant or product. So stoichiometry. So first I just want to talk about our chemical reaction, and let's just do iron plus oxygen going to iron 3 oxide. So when we balance this one, I need a 3 in front of oxygen, a 2 in front of iron 3 oxide, and then a 4 in front of oxygen. And then remember those coefficients. Right? They're the numbers that I just put in front of our species in our chemical reaction to balance it. And they can represent 2 different types of things. So one on a microscopic level, we could say that for every 4 atoms of iron, I need 3 molecules of oxygen, and that's going to produce 2 compounds of iron 3 oxide. So those coefficients can represent the number of atoms. If I had an ion, it could represent that, compounds, molecules, etc. Right? So 4 atoms of iron, 3 molecules of oxygen. So on a microscopic level, so right, something small that we can't really handle. On a macroscopic level though, something that we can go into lab and actually deal with, so something much larger, we can say that those coefficients represent the number of moles. Remember, moles were our SI unit for the amount of a substance. So the number of moles of each reactant and product. So if I went back up to that equation here, I could say 4 moles of iron react with 3 moles of oxygen to give me 2 moles of iron 3 oxide. And they represent both of those. We just use either the microscopic or macroscopic version, depending on what we're trying to solve for, right? If I'm trying to solve for the number of compounds, then I want to talk about the number of atoms of iron that go into it. If I want to figure out how many moles of my compound I'm producing, then I'm going to talk about how many moles of iron we're starting with. So microscopic and macroscopic level, it does represent both of those things, and the one I use just depends on what I'm trying to solve for. In the stoichiometry section, we're generally going to be focusing on the mole portion, so we can say that those coefficients are mole ratios. Basically, how many moles of everything do I need for my balanced equation? So in this equation, 4 moles of iron, and I'm just going to put equal signs, right? For my reaction to occur, for every 4 moles of iron, I need 3 moles of oxygen, and then that's going to produce 2 moles, didn't leave myself enough room here, of iron 3 oxide, right? I'm thinking those as ratios. So if I wanted to convert from one to the other, I can actually just use these coefficients as ratios. Right, my 4, my 3, and my 2. I'm just double checking that I copied them down right. So an example for us. If 6.472 moles of iron are used, how many moles of oxygen are needed? And again, I'm just using those coefficients as my conversion. So because I'm only talking about iron and oxygen in this example, those are the only coefficients I need, right? I know for every 4 moles of iron, I need 3 moles of oxygen. And then we're going to solve this problem just like we did when we were converting between units. I'm going to use dimensional analysis. Remember, dimensional analysis is where we use equalities. So 4 moles of iron is equal to 3 moles of oxygen. That's an equality, right? Those two are equal to each other for this equation in the form of a fraction. So 4 moles of iron over 3 moles of oxygen, right? Remember, if you have an equality in the form of a fraction, it's just equal to 1. And that would be the same thing as 3 moles of oxygen over 4 moles of iron, right? So when we were doing our dimensional analysis problems, remember we always started out with what was given in the problem, which is moles of iron. So that's the first thing I'm going to write down. So 6.472 moles of iron. And then remember, we're going to multiply it by our conversion factors so that our units cancel. So since I have moles of iron on the top, I need to have moles of iron on the bottom. So this is the version I want to use so that they cancel. So I'm going to have 4 moles of iron down here, and then 3 moles of oxygen on the top. When I do that, moles of iron are going to cancel each other out, and I'm going to be left with moles of oxygen as my units. So we're going to take 6.472, grab my calculator here, times 3, divided by 4, and that's going to give me 4.854 moles of oxygen. So that would be my answer. The 3 and the 4 are exact numbers, so I'm going to essentially ignore them for significant digits. Remember, exact numbers have an infinite number of significant digits, and we always want the smallest number in our answer when we're multiplying and dividing. So 6.472 is 4 significant digits. The 3 and the 4 have an infinite number, so 4 is smaller than infinity. So I want 4 significant digits in my answer. So let's do another example. This one's going to be a little bit different. So how many grams, not moles this time, but grams. So how many grams of iron 3 oxide are produced from 62.47 grams of iron? Right, so this time, instead of starting out with moles of one substance and solving for moles of another, we're starting out with the mass, and we're solving for mass in grams. Though we said the coefficients can represent 2 different things, one of those things was not grams, right? We said our coefficients can represent the number of moles of reactants or products, or they can represent the number of particles, right? How many atoms, ions, compounds, molecules do we have? But coefficients, do not, capital N-O-T, represent the number of moles. Or sorry, they do not represent the number of grams. They do represent the number of moles. They do not represent the number of grams. So I can't go directly using my coefficients from grams of one to grams of the other, because they are never going to represent the number of grams. What I'm going to need to do first is convert from grams of one to moles, then use those coefficients, right, my mole to mole conversion factor, and then back to grams. So how do we convert between grams and moles? We covered this in an earlier chapter. If we had grams of something and we wanted to convert to moles of the same thing, how did we do that? Yeah, hopefully you guys remember molar mass is going to be our conversion factor. So every time you have grams, you would use the molar mass to get moles. If you have moles, you use the molar mass to get grams. So if you want to go from grams of a substance to moles of that same substance, you're going to use molar mass. So grams of substance A to moles of substance A we're going to use the molar mass of substance A, whatever it happens to be. So a plan for this, let's write out our little plan. We're starting out with grams of iron, and I'm going to need to convert it to moles of iron. And to do that, we will use the molar mass of iron. Once I have moles of iron, this is where I can use my coefficients to convert to moles of iron 3 oxide. To do that, we use the molar mass of that substance. Oh, sorry. Wow, I'm not off to a good start this morning. To do that, we will use the coefficients. Anytime you go from moles of one substance to moles of another, the coefficients are going to be that conversion factor. Once I get moles, then grams, and to do that, we will use the molar mass of iron 3 oxide. So grams to moles using our molar mass, and then moles to moles using my coefficients, and then moles to grams of my new substance using the molar mass of that new substance. So every time we go between grams and moles, we're using that molar mass. Every time we go between moles of one substance, so moles of A to moles of B, we're going to use those coefficients. Right, in our balanced equation, of course. So I'm converting between grams and moles, I'll use the molar mass, right? I'm converting between moles and moles, I'm going to use those coefficients, and then moles back to grams using the molar mass. I'm going to rewrite that equation down here because it's so far up, I don't want to keep scrolling on you. So iron plus oxygen going to iron 3 oxide, and then I had 2 moles, 3 moles, and 4 moles. I'm in a really bad habit about not writing states of matter, but you should write states of matter when you're doing that. So my coefficients 4, 3, and 2. And then I guess we do need to scroll back up to get our problem. We had 62.47 grams of iron. So 62.47 grams of iron, just so I don't have to keep going back up and forth. So let's calculate our molar masses. We do need the molar mass of iron, so I'm grabbing my periodic table here. And since it's just plain Fe, is coming right off the periodic table. So my molar mass for iron, let's just write it above iron here. I get 55.85 grams per mole. Remember, I do want you to carry out at least 2 digits after the decimal point. If you want to carry out more, that's fine. On our course periodic table, it is 55.845. So if you want to carry out that extra digit, that's fine. But if you're going to round it, no fewer than 2 digits after the decimal point. We do need the molar mass of my compound here, so that's going to have 2 iron. Remember, when we're figuring out the molar mass of a compound, it's the sum of the molar masses of all of the atoms in that compound. Oxygen, I have 3 of them. And again, I'm rounding it to 2 digits after the decimal point. If you want to carry out more, that's fine, just not less than that. So I'm typing that into my calculator here. And I got 159.70 grams per mole. Remember, when we're adding its digits after the decimal point, so when I plugged this into my calculator, I actually got 159.7, but I know that I have 2 digits after my decimal point, so I needed to add that extra 0. Okay, now we're ready to do the problem. So I always start with what's given. which is my 62.47 grams of iron. Since grams of iron are on the top, remember we're doing dimensional analysis here, grams of iron have to go on the bottom. So my molar mass up here, I want to put the 55.85 grams on the bottom so that it cancels. Right, and that's for every 1 mole of iron. And you don't have to put the 1 there. I often don't. I'm just making a point out of it. So grams of iron cancel. I'm now left with moles of iron. I now need to convert to moles of my compound, right, moles of my product, and I'm going to use the coefficients of my balanced equation to do that. I know for every 4 moles of iron, I'm going to produce 2 moles of iron 3 oxide. In my dimensional analysis problem, since moles of iron are on the top, moles of iron have to go on the bottom. So 4 moles of iron over 2 moles of iron 3 oxide, and then moles of iron cancel. I now have moles of iron on top. I need that to go away, and grams of iron 3 oxide. So I'm going to use my molar mass of iron 3 oxide. Since moles are on top, the mole is going to go on the bottom. So the 159.70 grams goes on the top, and moles go on the bottom. And moles now cancel. So I'm going to grab my calculator. Remember, everything on the top gets multiplied, and then it gets divided by everything on the bottom. Order of operations with multiplication and division, it doesn't matter what order you want to do it in. And I got 89.31 grams.